Hello and welcome to the AI Research Roundup. I am your host, Alex. Today is May 10th, 2025, and we are looking at a paper from Hugging Face's trending list, published just 4 days ago, titled Geospatial Mechanistic Interpretability of Large Language Models. This paper introduces a framework for geospatial mechanistic interpretability, basically using spatial analysis to understand how large language models internally handle geography. It looks at internal signals called activations, and uses spatial autocorrelation to see if nearby places trigger similar activations. Since these activations can be polysemantic, meaning one part encodes many ideas, which aligns with the superposition hypothesis that networks encode more features than neurons. They use sparse autoencoders to find clearer, single-concept features. Alright, so this first figure visually outlines their whole process. At the top, you see a large language model, or LLM, taking in a place name. From inside this LLM, they extract those internal activations. The bottom section then illustrates their core method. They apply spatial autocorrelation to these raw activations to check for geographic patterns. And then, to deal with those potentially mixed-up polysemantic signals, they use a sparse autoencoder to get cleaner features, and then they run spatial autocorrelation on these refined features too. This helps them see how geography is represented. Okay, so building on that method, these maps here visualize those raw activations from different large language model layers. We are looking at the UK, Italy, and some US states. For each region and layer, we see the raw activation values on the left, and on the right, maps showing local spatial autocorrelation, which highlights clusters where nearby places have similar activation levels, like high spots. Crucially, these also show how activations can be polysemantic. For instance, one neuron might light up for both New York State and Northern Ireland, demonstrating that a single internal signal can represent multiple, sometimes quite different, geographic ideas. So after seeing how those raw activations can be polysemantic, or represent multiple ideas, this next set of maps shows the results of using that sparse autoencoder. We are still looking at layer 15 for the UK, Italy, and US states. Each row here shows a different feature extracted by the sparse autoencoder, with its activation values on the left and spatial autocorrelation clusters on the right. The aim is to find more monosemantic features, that is, features representing a single, clearer geographical concept. For instance, one feature strongly highlights southern Italy, appearing quite monosemantic, while another seems to capture the general concept of city. So, even though those sparse autoencoders helped find clearer geographical concepts like southern Italy or urban areas, it is quite telling that only a very small fraction of these extracted features actually showed strong spatial patterns. This really underscores that large language models seem to encode geography in a very distributed and often subtle manner. Overall, this approach, combining spatial analysis with mechanistic interpretability techniques like sparse autoencoders, offers a promising path to better understand how these complex AI systems internally map our world. This understanding is super important for developing more reliable geo-AI applications. That is all for today's AI Research Roundup. Thanks for tuning in.